really excited to have Volodymyr Kuleshov join us today. I personally got to meet Volod when he was still a PhD student at Stanford, and I was an undergrad. He was like all the work that he does is so impressive. I really looked up to everything he did. So Volodymyr Kuleshov is co-founder and chief technologist at Fresh, a startup focused on reducing food waste and in the food supply chain using AI. And he's an assistant professor now at the Jacobs Technion Cornell Institute at Cornell Tech in the computer science department at Cornell. He obtained his PhD in computer science from Stanford University, where he was recipient of the Arthur Samuel Best Thesis Award. His work focuses on machine learning and its applications in health and sustainability, and has been featured in Nature Biotechnology, Nature Medicine, Nature Communications, and Scientific American. And he's also awarded an NSERC postgraduate fellowship and a Stanford graduate fellowship. So I couldn't be more excited to let him kick off our CompSys DC 2022 conference keynote. All right, Volod, take it away.
Thank you, Chris, for the introduction. It's really my pleasure to be here. And just to make sure I time myself properly, until when should this go? So I think we're starting 5 minutes later. Do we still finish at the same time, which was, I guess, 12:05 Eastern?
You could take, we have a break scheduled after, I think. So feel free to take a little.
All right, I'll try to finish at the hour if that's fine. Then, so that we're okay. I assume it's fine, or we can go a little bit longer with questions if you want. Sounds good. Okay.
Sure.
All right. Well, again, thank you for having me here.
Sorry to interrupt.
Yes.
Do you want to take questions as people have questions, or do you want to wait till the end?
I think it's fine.
Make that.
If folks want to ask questions.
Okay.
Yeah,
okay. We'll
the only thing is I might not see you, so maybe if somebody could raise a hand or something like that. Mm-hmm.
Yeah, guys, just raise a hand or put it on chat, and we'll monitor the chat. Thank you.
Okay, well, again, as Chris said, my name is Volodymyr. I am a co-founder and chief technologist at Fresh, and I'm also faculty at Cornell Tech and Cornell University. And in this talk, I would like to tell you about how machine learning and AI can have an impact on an important environmental problem called food waste. And so to start, I would like to tell you about food waste itself. What is food waste? So the sad truth is that in the US, about 30 to 50% of all the food that is produced ends up being discarded. It ends up being wasted somewhere before it is consumed. And this is a massive, massive, massive problem for society. Just to give you an idea of the magnitude of the problem, I have here some numbers. So if we were to calculate the value of all this food that is being discarded, by various estimates, it's something on the order of 400 billion, $500 billion of value that is lost because of food waste. And again, just to give you an idea, that is roughly 2% of US GDP that is lost on wasted food. So this is a huge problem for the economy, and at the same time, it's a huge, it's a societal problem, especially from the point of view of fairness, because while all this food is being discarded, about 1 in 6 Americans remain food insecure. So there's still not everybody has enough food, and yet we're wasting almost half of what we're producing. And I will be citing a lot of numbers like this throughout the talk. I just want to immediately tell you my source, which is this consortium called ReFed that you see at the bottom. ReFed is a consortium of various organizations, including commercial companies, so supermarket chains, as well as NGOs. And the goal of ReFed is to study and understand and make plans for how to resolve this problem of food waste. And they have a very good guide that they make every year where they can compile a lot of statistics and propose policy changes that is available on their website. And a lot of the contents here on the slide are coming from that source that has been thoroughly researched. So food waste is a huge societal problem, and it's also an important environmental problem. Producing all of this food that is ultimately discarded is using a lot of our resources. So in order to create the food that we eat now, we essentially need twice the resources that we normally should use, because so much of the food is lost before we actually get to consume it. And so again, just to give you an idea of the magnitude of the problem, so in the US, food waste is responsible for 4% of greenhouse gas emissions, 14% of freshwater use, 80% of all cropland use. It uses a lot of landfills, and it's just a very, very inefficient use of our resources that ultimately significantly hurts the planet. And specifically, food waste is a big driver of climate change. It's a big factor, and it's a big lever that we can use in order to influence climate change. So creating all of this uneaten food uses, as I said, a lot of resources and a lot of energy, to grow it, to build the fertilizer that is used to create the fertilizer that is used to grow this food, to transport it to various places, and then it spoils along the way. So this uses a lot of energy, and this use of energy has a lot of impact on climate change. So the one famous statistic is that if food waste was a country, it would be the third largest greenhouse gas emitter behind China and the USA. So its greenhouse gas emissions would exceed those of Russia, those of India, those of Japan, and so I hope this gives you a sense of how problematic food waste is for our society.
Hey, quick question. In this chart, is this food waste from global or just US, or?
This would be global food waste. Yeah, global yeah, the amount of energy, the amount of food that is being thrown away globally. If that was a country, it would be the third largest in the world. So where does food waste happen, and why does it happen, is the question that I want to ask next. And again, ReFed has done a lot of research on this topic. So food waste can occur at the farm. It can occur during while transporting the food from the farm to various manufacturing facilities or processing facilities, or while it's being transported to stores. It can be wasted during those it can be wasted at those processing facilities, as well as then at the last stage it gets shipped to consumer-facing businesses such as restaurants or supermarkets, and then homes where the food is consumed, and it might be wasted at home because it stays too long in your fridge. So ReFed did a bit of a breakdown by area, by sector, to understand where food is occurring. And this is, you see overall the breakdown on the slide. And the thing I want to point out immediately is that a lot of it is happening in consumer-facing businesses and downstream. So by this, I mean restaurants, supermarkets, and then at the homes of the consumers that go to these, for example, supermarkets and buy that food. So the consumer-facing and downstream sector plays a big role in food waste. And if we were to impact that sector, that part of the supply chain, and try to reduce it, and try to reduce waste in that sector, that would have by itself a very significant impact on climate, on sustainability, and in terms of reducing economic losses. For example, a 25% reduction to US grocery food waste alone would eliminate tens of millions of tons of greenhouse gases every year. it would conserve billions of gallons of water, and it would recover many millions. It would recover many meals that can be used to feed the people that currently don't have access to fresh to quality food. And so how can we impact food waste? How can we, what can be done? What are the main levers that can be used in order to reduce food waste? Here again, I have a screenshot from from what's called the solutions database that again was created by ReFed. If you go to this URL that you see at the bottom, ReFed actually has a very interesting interactive website where they can share, where they have shared various strategies that they have identified as having a lot of a lot of potential impact on reducing food waste. And this is a list. This is actually a screenshot from their website that I just took directly. And these are the main ways that they have identified in terms of reducing, in terms of the main strategies for food waste reduction. And if you look at these, let's look at a few topics on this list. So there are things like enhanced demand planning, decreased transit time, intelligent routing, markdown alerts, strategies for properly processing the food in a first expired, first out manner. What's interesting is that a lot of these strategies are actually there are problems that have the flavor of operations research, right? So demand planning, intelligent routing, intelligent optimization. These are all techniques that involve more efficient supply chain planning and more higher optimized. This involves better optimized supply chains. And these are also problems that can be addressed using technology, right? I think what's exciting about this list is that a lot of these problems are ones where we as computer scientists are able to have an impact via more efficient technological approaches and more efficient planning and optimization approaches to the supply chain, right? So enhanced demand planning, that means understanding and predicting where demand will occur and planning for that demand. Routing is a classical optimization problem. Markdowns are another classical optimization problem. So there's a lot of problems where computer scientists and researchers like us can significantly have an impact by designing better, more intelligent mathematical and machine learning and algorithmic techniques for optimizing various supply chain processes and, of course, implementing them in the real world. Just to give you an idea of why they are identifying these problems as having high impact, let me show you an example of how supply chain operations currently work if you were to go to a supermarket, for example. So these, what you see here, are what are called ordering sheets from a large supermarket with billions of dollars in revenue. And essentially, these sheets are used by the store to figure out every morning how much food they need to stock in order to meet their demand for the next several days. And this is in the produce department where the food is highly perishable. And so essentially every morning, there is a person that operates the produce department in a supermarket. And usually it's a person who, it's the same person that stocks the shelves. It's the same person that might help you find, if you're looking for some kind of avocado, they will help you find that avocado. And another big responsibility that they have within the supermarket is to plan how much, it's basically to do inventory planning. So every morning they get faxed these paper sheets, and then they walk around the store, they count how many cases of tomatoes they have, and then they try to, using their intuition, estimate how many more cases of tomatoes do I need in order to meet my demand for the next few days. And then they write it down on their sheet. They might see what they ordered before, so then they might know what's coming in over the next few days. They can use that to adjust their decision. But essentially, using this highly manual pen and paper system, they make one of the most important operational and supply chain decision that that their store needs to make. And of course, it's really hard for a human to make these operational decisions for hundreds up to thousands of items that they own within their department. It's just not something that they can that they're good at. So they need to anticipate how much demand they will have for hundreds of different items, and then guess that, and then put that into the into their sheet and order that. And it's just not something that a human is good at. So this existing pen and paper system is highly inefficient, and as a result, they really don't want to have a store where they're out of different items, where they're out of tomatoes or out of bananas. Therefore, they tend to order a lot, and supermarkets easily have double-digit waste numbers as a result. So this is an example of how inefficient manual supply chain processes are significantly contributing to food waste. And this is also an opportunity for doing something better using modern machine learning and optimization and software technology algorithms. And so this problem of applying technology throughout the supply chain and applying machine learning throughout the supply chain to reduce food waste is what I want to focus on in this talk. And in particular, I would like to talk to you about this company, Afresh, where I'm a co-founder, where we have been developing automation systems for problems like the one I just described. And the goal is to significantly reduce food waste by injecting machine learning and AI throughout the food supply chain, making the food supply chain intelligent, more efficient. And this is a company that came out of a research project at Stanford. So it's also closely related to a set of research topics that we have been looking at. And I will also talk to you about some of the research challenges that we had to solve, some of the kind of core machine learning algorithmic challenges that we worked on while we were developing this applied real world system. And so this is something that came out of a research project in 2017, and then now the company is actually over 100 people, and it has received multiple rounds of funding, and it is deployed in hundreds of stores. And by the end of the year, this will be this system that I'm going to describe will be deployed in thousands of stores. So this is actually a set of this is actually research that found its way into real world applications and into a real world deployment. So what is the system? What is the solution that that Afresh develops? And let's look at it first right now from the point of view of the user, of the supermarket operator. So essentially, one of the core offerings of the company is a dashboard that runs on a mobile device, on a tablet, that automates this highly inefficient pen and paper processing system that I just described. So instead of having to go through the store and take notes on this piece of paper and decide how much to order on a paper on a piece of paper, now we replace these sheets using an iPad that runs something that looks like a digital version of these sheets. And so they can do everything through software, and they can order directly through their tablet. And then this tablet presents them their familiar interface. And you can think of this tablet also as being kind of a control center for the entire store. So it's a dashboard where they can digitally make all the decisions, all the operational decisions that go into running a store. And crucially, this interface, this tablet, is connected to a machine learning engine that lives in the cloud. And the machine learning engine determines how much they should order, as well as any other important operational decision that they need to make. And so instead of now having to use their intuition to determine, oh, let's say I need to buy this many cases of tomatoes for the next several days, the system will provide a recommendation, and their role is only to accept or reject this recommendation. So this is the interface that I just showed you. And next, I want to look at how this works underneath the hood. And as I said just now, this system is connected to this tablet is connected to a machine learning engine that runs in the cloud. And this engine recommends decisions, in particular decisions for inventory control. So what is inventory control, and how do you actually formulate this using the language of machine learning? So again, here on the left, you see a person that is using the system within a supermarket department. And essentially, this problem of inventory control, we formulated as model-based decision-making, or model-based control, or model-based reinforcement learning. And so what do I mean by that? The input data to the system is their historical time series that describe their historical sales, their historical shipments, their historical prices, their historical orders. All of this data goes into building a probabilistic model of the future. And the key future event that is important to model here, that will be the focus of this talk, is their demand. So we want to know in the future, given the current state, and the state can be described by the prices and the history of behavior by the consumers. Given the current state, what is going to be my demand for the future? And the modeling part, or the model-based part, is about creating a predictive model that will output a distribution, a probability distribution over this future demand. And then the control, or the planning part, is the idea that given these predictions of the future, we want to determine actions that are good under this model, in the sense that if the agent or the system makes certain decisions, let's say it makes certain ordering decisions, then we want these decisions to have a good expected utility under the model. So if the model outputs a certain distribution over demand and we make certain orders, then the expected future state under the model will be maximizing the utility of the system, which is something that we get to define. And then these recommended decisions are surfaced back to the operator. So this is the overall framework that we're applying in order to translate the inventory control problem into machine learning language. And so I'd like to talk to you a little bit more about the challenges of each of these components. What are the main technical challenges that involve building out these two components? Well, the main challenges on the probabilistic predictive modeling side and on the model-based control side. So on the predictive side, essentially it's a supervised learning problem where we need to estimate, where it's really crucial to estimate the uncertainty of our predictions using the language of probability. And this task, again, as I mentioned earlier, we have our raw data consists of historical time series, so all their historical sales, their historical prices, shipments, orders, and this is a really big data set. The typical deployment involves hundreds of stores, involves potentially thousands of items, and then several years of data, which is thousands of days. And if you multiply all of these numbers, that means there's about there's tens to hundreds of millions of data points, where each data point is a particular is a prediction that needs to be made for a particular item in a particular store on a particular day. So this is a really, really big data set, and it requires machine learning models that scale. And some of the approaches that have been taken here are really focused on deep learning, which benefits from these large data sets. So on one hand, we have this large data set, but also on the other hand, there are various predictions for which we don't have enough data. For example, certain holidays, which are really important for making decisions, are found very few times. So for example, each item we'll see, so for example, Turkey on Thanksgiving, if you have 3 years of data, you only see 3 instances of Thanksgiving in your data set. So even though there are a lot of data points overall for certain key events of interest, like holidays or certain price changes, or maybe when a new store opens, there's actually very few data sets for very few data points for these key events. And so this requires using more complex multitasking models that consider all of the stores and all of the items jointly within the same model. And so for example, if there's only if for Cinco de Mayo there's only a few instances of that, but you have sales of limes for different stores, then it's possible to train the same model that will kind of solve this task, solve this prediction task for multiple stores jointly and benefit from multitask training. There's a question.
Yeah, so I imagine there's this issue of censored data, right? Because it's hard to estimate demand after a product has, completely, after a product is sold out. And also, at the risk of slightly getting ahead of, I know you'll define the decision-making problem, but I'm interested to know the utility, how you define the utility function, because the decision point that minimizes wastage doesn't maximize sales for the store necessarily, right? I mean, you can always under order and minimize wastage.
Yeah. So your first question is sensor demand. Yes, that is true, and the magnitude of this problem or the importance of this problem depends on how often the store runs out of certain items. Fortunately, in the historical data, they tend to overorder, so the store actually runs out of items rarely, and so sensor demand is actually not something that we found to be traditionally extremely influential in terms of the performance of the system. However, we also have developed techniques based on imputation, missing value imputation, that try to detect and fill in sensor demand in a pre-processing stage before training. But that's a really good point. And then your second question was about the objective function. And yes, you're right that if the goal would be only to minimize waste, then you just don't order anything, and that it trivially minimizes waste. Of course, we don't want to do this. And so there has to be a discussion with the user of the system, which is typically a large enterprise company, in terms of what are the things that they care about. And the objective function has to involve, it has to also involve their profits. But of course, maximizing profits and reducing food waste is extremely correlated, because anything that is wasted, that is directly a hit to their bottom line. So they definitely lose a lot of money on every wasted item. And so they're really incentivized to reduce waste, but it's not the only consideration. They also need to still sell something. And so there is it can be, you can think of the objective as being a weighted combination, for example, of waste and profits, for example. Well, no, it's not true. It can be, actually profits is a really good one because it implicitly also minimizes waste.
Great, thanks.
Yeah. So these are some challenges that are faced on the machine learning, on the predictive modeling side. And the last one that you see here is the probabilistic aspect that I said, that I briefly alluded to earlier. In order for these predictions to be used downstream for decision making, as well as in order for them to be more interpretable by the users, it's really important to output not just a single point estimate, but rather a probability distribution over the event of interest. And that's the probabilistic modeling question that we're interested in here. So this is just a high level overview of some technical challenges. I will dive deeper into one or two challenges a little bit later. Here, I just want to give you an overview. Similarly, the decision-making component, as I said, and as we just talked about, it has to account for a number of objectives, which are decided together with the user. Another one that I haven't mentioned is the shelf appearance. So if the shelves are always dangerously close to being empty, even though they're never technically empty, but it's never good if you only have like one item left. It just looks bad, even though technically you're perfectly matching supply and demand. So that's an additional set of constraint that has to be decided with the user. It's a different objective that has to be decided with the user. And also, the decision-making problem is faced under a lot of constraints. Has to be solved under constraints. For example, various constraints on how certain inputs have to be shipped together, various possible delays in expected delivery times. And also, these decisions have to be made in a partially observed environment. For example, the data that we have, it never tells us what is the actual waste. We only see shipments and sales. And also, we don't observe the quality of the items. So certain items might arrive with some amount of shelf life. Another item might have less shelf life. That's an important variable that is unobserved. We don't observe the inventory levels. And so to solve all of these problems, we again, I guess the key kind of technical, the framework that we use is that of model-based control. So after the prediction has been made by the model, we have to solve an optimization problem where we optimize the expected value of the objective subject to all of these constraints. And there are some interesting optimization challenges that arise there. And at the same time, these decisions also have to be ultimately used by users downstream. So it's important to calculate things in a way that will be interpretable and that will build trust by the users ultimately. So as I said earlier, these decisions are surfaced in a system that looks as follows. So there's a specialized system that was designed. I guess this is not an AI system that runs in isolation. It runs very closely with a human. These human operators need to trust their system. They're often used to doing the pen and paper approach, and they have been following that approach for possibly decades. They're also typically not the most tech forward. They might be a little bit hesitant to use technology. There's some concerns about automating them away. So that already builds some initial mistrust. And so it's really important to be thoughtful and really think about the design aspects of this system and this interface in order to make sure that it's still familiar, that it builds trust, that it's, these are some of the challenges that are that arise on the human interaction side. And again, as I said earlier, this some of the machine learning ideas that we implemented here have been based on research that we have been doing at Stanford, both before the company started and after the company started. These are research. These were research projects on decision making under uncertainty, and in fact, some of this research, even after the company was started, was published at ICML in this example. So we have a few papers. Here are two examples of papers that we published at ICML 2018 and 2019, and these explore some kind of core machine learning questions that are closely motivated by the problems that the company was working on. And so I'd like to tell you a little bit more also about what this research is about and how it connects with the applications that we're working on. And one of the main questions that we raised in these papers is the following, which is what uncertainties are needed in order to perform effective decision making? If we're making let's say that we're solving a simple binary classification problem. There, when you have a classifier that outputs some kind of value, we ultimately it's really simple to understand what makes a good classifier or not, or it's typically relatively simple. We usually care in something like the classification accuracy, which is essentially how many correct predictions you made out of the total number of predictions that you made. And there might be some precision recall trade-off or specificity sensitivity. There might be some ways of breaking out the objective, but ultimately in a standard predictive task where we just output a prediction and we think of it as some kind of binary prediction, the evaluation of what is a good prediction is relatively easy. However, when we are in a probabilistic setting and when we output an entire distribution over future predictions, there the question of what makes a good distribution is much more ambiguous. So there's no simple metric such as let's say classification accuracy that we can use. I mean, we can use, but we would be ignoring various aspects of we would be ignoring the fact that our prediction is a probability distribution. And so the question of what makes a good probabilistic prediction it's much less well understood. And there are some important nuances into how we reason and how we think about what makes a good probabilistic prediction. And so in some of this work, we revisited this question from the point of view of some classical statistical theory on what is called proper scoring rules. And essentially this theory identifies two specific key characteristics that determine what is a good probabilistic prediction. So normally, when we at least train our models, we use an objective such as the log likelihood. Let's say we want to have a predictive probability over y, then we look at the expected log probability over y under the model. We look at the log probability of the data under a model. So the likelihood is definitely the objective that we use the most often, and it's also what we then often report as our metric after we have trained the model. But the log likelihood by itself doesn't necessarily mean that a probabilistic model will work well for different downstream applications. And I guess that motivates the question of what actually does the likelihood measure? And according to various kind of lines of research and statistics, we know that actually objectives such as the log likelihood measure a few specific things. In fact, we can think of the likelihood as decomposing into two key properties that define a good predictive forecast. The first one, which can be characterized, I guess the mathematical term would be the KL divergence between the model and the following auxiliary distribution, but maybe the math here is less important. The first term of this two-term decomposition of the log likelihood that I will show you is something that is called calibration. And that just means that intuitively, it means that when I predict a probability distribution, then if I take each confidence interval, say the 60% confidence interval of my predictions, then the true outcome will be contained in that interval 60% of the time. So here, this red curve is my predicted distribution over y, and at the bottom, these blue circles are the events. And so the 60% confidence interval, which I'm illustrating here with these two vertical bars, it contains 6 out of 10 outcomes. And of course, these outcomes would be realized over time, over many samples from the true distribution, from the true data distribution. And if I were to sample many times from the true data distribution, my 60% interval would contain the true outcome about 60% of the time. So that is one desirable property that we want to have. And the other one is something called refinement, which means that these confidence intervals, every confidence interval should be as tight as possible. So the 60 confidence interval and the 80%, basically the delta, our prediction should look as closely as possible to a delta function, and it should be calibrated. And of course, if these two properties hold, then we have essentially a perfect forecast. And by the way, this refinement term, it can be formalized as the entropy of this predictive distribution that I mentioned, which is the distribution of all the confidence intervals. And the sum of these two terms can be shown to equal precisely the log likelihood. So the log likelihood has this decomposition into two key characteristics. And if these two characteristics hold, then we have a perfect forecast. Yeah, okay, there's a question.
Hi, Vlad. Just a quick question on the notation. Can you explain a little bit this on the bottom right of the slide, this P data Y given this P theta of X?
You mean Q, right? So Q of Y given X. So Q of Y given X is the distribution that is conditioned, is the distribution of Y conditioned on a forecast of the model at X. It's easier to understand in the binary case. Let's say that you have a binary classification and you output the probability of the event occurring as being 80%. Then your prediction at X is 80%. And then you're looking at the distribution over Y conditioned on your prediction, which was 80%. So the probability distribution of Y conditioned on predicting 80%, the probability of Y equals 1 conditioned on the prediction that Y equals 1 is 80% should be 80%. That's kind of what this Q is doing, but of course this also extends for an so this prediction from the model. So this actually extends when beyond binary classification. And let's say you output, like, your prediction is a Gaussian, like I output my prediction to be a certain Gaussian with a certain mean and a certain standard deviation. Then condition on that, the actual data should also have the distribution. And so this is why we're looking at the expected KL divergence between the actual distribution condition on that forecast and the forecast itself. And we want the forecast, we want condition on making a forecast, we want the Y to have the probability of Y to be the same as the forecast that we have made. It's not particularly, I guess for the purpose of this talk, it's not really important that we understand the math. Maybe I should have not put the math here, but this is just, I think the key idea here is that actually there are two defining characteristics that that determine what makes a good probabilistic prediction. And those are the characteristics that we are optimizing for when we optimize the log likelihood. And these are called calibration and refinement. And then that raises the question of, are these two objectives equally important for tasks such as decision making? And some of our research has argued that no, actually, they're not the same. And calibration is much more important than refinement. And this is illustrated by the following example, where let's say you have a self-driving car system, and the self-driving car system, well, it uses a model to determine where, let's assume for the sake of this argument that it uses a model to determine where it will go after it has, let's say it applies the accelerator or the brake or it turns the wheel, then its internal model tries to predict where the car will end up at the next time step. And if this, if the uncertainty of our prediction is not sufficiently accurate, and if we're either overconfident or underconfident, then this can lead to bad decisions, like you see here, where you could have a really bad event, such as a crash with this pedestrian. So in purple is the distribution of the model of the car, where it thinks it will go if it makes a certain move, and then the green one is where it thinks where it will actually go if it performs that sequence of actions. And here you see that if the estimate of the uncertainty is incorrect, if the distribution is miscalibrated, then we can have a bad outcome. This is the intuition of our argument. And in our ICML 2019 paper, we actually formalized this a little bit more. And we actually have a formal argument that if we start with if we wanted to compute the expected policy, the expected value of a policy, right? So if we're in a Markov decision process where we are running a certain policy and we want to estimate the value of this policy, which is defined as the value of a certain state plus the discounted probability of the next state to which we transition if we perform an action under the policy, and then we have a set of dynamics which determines the next state where we will end up given our current state and the action that we have decided, and then we take the expected value of all of that, and this gives us an expected value for the policy. And the idea is that if these we might want to estimate this by learning the transition function, and then we know the policy, we know the transition dynamics, and we can try to implement this, and we can try to compute this the value of any given policy. And let's say we do, I don't know, value iteration or some kind of simple algorithm for learning these policies. Well, when will our learned transition dynamics provide us a good estimate of the value of this policy? That will happen when they are calibrated. So calibration is a sufficient condition for obtaining accurate estimates of the true value of the policy. So if we plug into this formula any estimate of the true transition dynamic that is calibrated with respect to the true transition dynamic, and I'm also hiding a lot of details under the rug. I haven't made the precise definition of what it means to be calibrated in this context, but intuitively, we can formally show that this is something that's sufficient in order to get good estimates of the value of the policy. This is kind of the more mathematical version of the intuitive argument that I made on the left hand, on the left side of the slide. And more generally, calibrated uncertainty decision-making is interpretable if we want to make, is important if we want to make interpretable predictions, if we want to be maximizing the reward. It's also important to balance exploration and exploitation, and right, because we often want to guide our exploration and visit more the areas with higher uncertainty. So better estimates of uncertainty also help us better balance exploration and exploitation. And overall, it helps us also make safer decisions and avoid, for example, the bad outcome that we have here on the left. So even though I guess a probabilistic model it's usually trained to maximize the likelihood of the data, there's actually these two important objectives: calibration and refinement. And calibration happens to be more important than refinement for a lot of these decision-making tasks. Now, a question is, are existing models typically calibrated? And in some of our work, we show that it's not. If you take, so for example, here, this is the result of training a Bayesian neural network. And if we visualize its 90% confidence interval in a particular region, well, actually 90% of the points fall outside that confidence interval. And if we, so it's typically highly miscalibrated and overconfident. It's a fact that is well known about machine learning models and especially neural networks. If we, but we also propose an algorithm that can correct this post hoc and ensure properties and ensure predictions that have the properties that we need. So this technique that we proposed, which essentially is a way of constructing a model whose calibration term can provably go down to 0. It follows an approach where there is some kind of baseline system that takes an input and produces a forecast. And you can think of this forecast as being a cumulative distribution function, or you can think of it actually even as being a density function. And then our algorithm provides a way of constructing a special model called a recalibrator, such that when we compose the recalibrator with a forecast, we get properties, we get forecasts which possess this calibration property. So let's just quickly look at what is calibration in this context. Let's say that we're doing binary classification. So this formula gives you an intuition for what calibration is. And it's what I alluded to earlier when Chris asked his question. here, this is the definition. And what you see here on the right is the probability of having the event y equals 1 conditioned on us making a prediction of p. And we want this probability of y equals 1 conditioned on the prediction being p. We want that to equal p, which is the definition of calibration in a binary classification setting, and it becomes more complex in other settings. And then from that, we can derive a simple formula for the ideal recalibrator, which is, so this recalibrator, R of p, for each p, it estimates how many times we observe the event y equals 1, conditioned on the times when the prediction was p. And so this is, if you stare at this a little bit, you should convince yourself that actually this is the ideal recalibrator. And essentially what this does is that it empirically measures the frequency of the event of interest for each confidence interval. And then given a new prediction, it remaps its predicted confidence level to the true empirically observed confidence level. And so if we can learn this RFP, where, by the way, capital P here is the data distribution. So this is a function of the data distribution. If we can estimate this conditional density, then we can perform recalibration, because this is the ideal recalibrator, and the algorithms that we've been discussing are that we propose in this paper are ways of learning such conditional density functions. Okay, so this is the method I wanted to show. And then we actually tried these algorithms on both standard tasks and on both standard benchmarks and reinforcement learning called, so for example, Mujoko is something that we tried. This is the performance that we got. So here, this is one experiment where we compared our a calibrated model-based control algorithm on this half cheetah task, where you have to control this robot called, yeah, it looks like a half cheetah. It's a famous benchmark in reinforcement learning. And essentially, we were able to significantly outperform. Well, first of all, our algorithm is in green. In purple is the uncalibrated baseline, which was actually a paper from it was Nagabandi et al. NeurIPS 2018. It was kind of their neural uncertainty-based model-based control method, which was state-of-the-art at the time when we published this paper. And so then our method significantly improved over it. And both of these methods perform significantly better than soft actor critic, which is a model-free method. And eventually soft actor critic outperforms the methods that both model-based methods. That's actually the dashed line. That's soft actor critic at convergence. But these methods, because they're model-based, they're much more data efficient than the model-free algorithm. And the calibrated one is the most data efficient of all of them. And we also have results on other tasks, on other Mujoko environments, which you can find in our paper. And we also created a synthetic benchmarking task for inventory control, which was this problem that I talked about in the first half of the presentation. And there we can also define it as a model-based control task, where we have a state which describes our inventory position, and as well as other variables of interest, maybe the prices of the items and so on. And then there is a transition function where there is some kind of demand that occurs, sales occur, spoilage occurs, and also there's a decision, which is an ordering or a shipment decision that brings us to a new state, and so on. This process repeats. So this clearly defines some form of Markov decision process. It's a sequential decision-making task where our actions are the shipments, and the transition function between state is determined by the sales and the spoilage. And we want to optimize the reward, which in our experiment was sales revenue minus shipment costs, so basically the profits. And then this was solved using approximate dynamic programming methods. And as a result, both the waste and the profits were significantly better under the calibrated version of the same algorithm relative to the uncalibrated one. There's a question.
No, I was just pointing out that maybe this is a good time for us to see if there are any questions. We started a bit late, but we really want to have give people a chance to ask questions. So yeah, would that be fine?
Yeah,
now?
yeah, perfectly fine.
Okay.
I mean, I think this is the main technical part. There was like a small little demo at the end, but this is perfectly fine.
Sure. Okay. Thanks a lot. Go ahead. You can just unmute yourself and ask, Ishan.
Yeah. Hi. Hi. Hi, Volodymyr. That was a very interesting presentation. So I had a couple of quick questions. So in the first half of your presentation, you gave an example of rare events that you strategize for separately, and you gave the example of Thanksgiving. What about events like hurricanes? You don't necessarily know when they are coming, but you still need to plan for that. Is that included in your historical data input somehow?
Yeah, I think it depends on the hurricane. If it's like a once in 100-year hurricane, it will be a little bit hard to deal with that. I think the strategy is to featureize these events in a way that would let you extrapolate from maybe adverse weather that's not a hurricane to adverse weather that is a hurricane, right? So maybe instead of having a feature, I mean, yeah, so you basically have to have this in order for the system to work in this cases, you have to have the data and you have to feed the data into the system in the right way. So you have to featureize it in the right way. And probably if you had a feature, if you had a binary feature, hurricane or not, I suspect that will be challenging because, as you said, you don't have a lot of hurricanes in your data set typically, but you could, for example, try to be clever in terms of how you featureize it. And you could, have like wind speed be a factor or precipitation be a factor. And then you probably observed instances of high wind speeds and high precipitation in your data previously. And that could allow you to extrapolate to a hurricane that would have more precipitation than usual. That would be the hope, yeah.
Okay, and I think in that slide you had the demand as a function of time. Would you think it is also useful to have it as a function of space? For example, certain region of America might have a specialized demand for some products.
Yeah, and yeah, absolutely. You want to have as many features as possible, and you want these features to also define the physical location where the events are occurring. And so if they're occurring in, yeah, like, like I'm sure a store in Mexico and a store in, I don't know, Japan will have a very different set of demands for the same set of items. So yes, it's definitely important to do this. And you could, for example, yeah, you could take the zip code. For that, you could derive various social demographic features of the area where the store is, and then add that to your model. And so again, it's a question of cleverly featureizing your data set.
Right. And in your experience, does that affect how you represent the output uncertainty? I mean, you're going to a higher dimension space.
Well, the higher dimensions be in the input. Here we've been looking at predictive uncertainty over the prediction variable, which is here for each kind of time series. It's a one-dimensional regression task. And so in that case, the dimensionality doesn't change. But I can imagine that, for example, you might, for example, in the hurricane example, if all of your data was for a certain type of wind speed, and now you have something which is significantly outside that wind speed, then your model might start behaving strange because you're actually feeding in points that are outside the region where it saw its data. And there, it really, this is when you really want to start thinking about Bayesian approaches or ensembling approaches, where when the point is out of distribution, you want to start observing a higher predictive, basically wider confidence intervals in your predictions, because the models are really, yeah, because you are getting points which don't look anything like your input data.
Okay, thank you. Thanks a lot.
Yeah, Tarun, go ahead. Maybe we have time for a couple of more questions. Tarun, you can just unmute yourself and ask.
Okay.
you're not. I mean, I don't know if it's an issue at my end, but I can't hear you, Tarun. I mean, it's a very, yeah. Yes.
Yeah, my headphones don't work really well. Well, I guess I was just going to ask, and maybe you might talk about this in the future. The data for your algorithm, like, do you kind of do this already, or have any plans of doing this going forward to kind of make it real time, in the sense of like when someone like cashes out at the cashier with an item and they scan it, is that data going into your system, or is it only kind of the end of the day inventory stock and you're ordering it for the next day or something like that?
I mean, technically it's at the end of the day, but what you're describing could also be useful for other applications. It's probably not critical for the particular application that I described in this talk, but there are other ones where you might want to have some kind of live view into the state of your supply chain, even maybe not at the store, as well as, you're at the delivery level, and maybe some items are being late, or that maybe your deliveries are late, or maybe something is happening at the warehouse, and having this kind of live stream data would be really useful for understanding the state of the system and any changes in the state of the system as they happen. And then I think on the machine learning side, you would want to look at changes, and you would want to look at you would want to do things like outlier detection, or figure out how if anything is essentially do some kind of novelty or outlier detection, I can imagine.
Okay, thank you.
Thanks. Go ahead, Chris. Maybe I think it's we would love to take a lot more questions, but maybe we we have to give like maybe a couple of minutes of break before we regroup for the presentations.
Yeah. Actually, I'll let Neil ask his question, because
go ahead.
Maybe
I have a quick question. So, in terms of estimated losses that this system has prevented, do you have any statistics on that? Because I think the original claim is that this is going to help in food security. I'm wondering, like, also, okay, so this is good to have. So how was the experience from the retailer sides, like with whom you worked during the project?
Yeah, well, you can see it on this slide, and it's actually out of date. I think the numbers are actually significantly higher now. This was cumulative up to a couple of years ago, well, maybe like over a year ago. I think these numbers are now out of date by a year. I apologize, didn't get the chance to update this slide, but yeah, so the typical, maybe it's useful to think of it as a percentage, and that I mean, of course, it varies by store, by location, varies on what they were doing before, but our overall number is around 25%, which is a really significant reduction for our for these supermarkets. And then you can try to extrapolate this by volume. So right now we're at about 1% of sales volumes, and we're quickly approaching in 2022, 2023 to reach about 10% of US produce volume. And that can, I think, have a really, really significant impact. This 25% can have a really significant impact on overall food waste.
Cool, thank you.
All right. Thank you again, Volod. We don't have really time for any more questions, but I did want to ask Volod, if people do want to reach you with more questions, what's the best way they can do that?
You can send me an email, but also I'm happy to hang out more at the conference. Maybe you can tell me if I want to hang out and ask and answer questions. Maybe you can let me know when is the best way to do this.
I see. So we do have, I didn't mention this earlier, but we have for each of the, we've set up a gather.town kind of social space online that we hope people will be used during the lunch break and also during the dedicated networking session tomorrow.